All right, today we're going to talk a little bit about angular momentum, and more specifically, when do you apply it and how do you really apply it? So back in the momentum days when we had linear momentum or translational momentum, if you had mass and you had velocity, then you had momentum, because if you had mass and you were moving, you had momentum. But angular momentum is very similar. Your masses become moments of inertia and your v's become omegas, but you just apply it in a different situation. So momentum, we used to use pi equals pf, and we'd say, oh, if there's a collision or a collision in reverse, we're to use conservation of linear momentum. But angular momentum is just a little bit different, and so that's what we're going to talk about in this video here. So when do you apply concepts of angular momentum? And I just put down an object is moving in a circle, so it's spinning. You know, it's spinning, or it's moving in a circle of some type, and I should say circle, or you could have an ellipse or spin like that, an ellipse. So oftentimes if it's moving in a perfect circle, you're going to use uniform circular motion, and we can talk about that in a second. But if we're talking about like an orbit that's an elliptical orbit, conservation of angular momentum is going to be your best friend. All right, and the second thing, if you're talking about an object that has a moment of inertia and it's changing, that'd be a good tip off that maybe you're going to use concepts of angular momentum conservation. And even if it just has a moment of inertia, like a mass with it distributed amongst some radius there, that'd be a good indication that you might have to use conservation of angular momentum. Let's get started by looking at an example. I'm just going to scroll this down here. So our example right here today that we're going to start with is a planet orbiting with an elliptical orbit. And I say this keyword elliptical because in uniform circular motion, we would treat orbits just as a circular kind of orbit. We did uniform circular motion, and that usually gets the job done most of the time. But let's say you're talking about a planet that you can assume that it's very close to a circle. So let's say there's some planet that's got a highly elliptical orbit, and I drew it right here. You know my videos. Planet Laurentis is back at it again. So here's planet Laurentis. Named after me, of course, and it's going here, then later on it's there, then over there, then there, and you can clearly see it's not anywhere near a circle, it's an ellipse. So you can't use uniform circular motion when you're talking about an object that's orbiting in an elliptical fashion. And I made a little note here. Note, you can't use sum of the forces in the radial set equal to gm Laurentis mass of the sun over r squared, because picture this, gravity's pointing inward here, right? And you're far away, and then over here you're not quite as far away from the sun, so the force of gravity is changing, so it's not a circle. You can't assume it's undergoing uniform circular motion then, because your force is changing because the r is changing down there. If they ever say the e word ellipse, you're like, oh, okay, I can't use this physics tool, but I can still conserve angular momentum, and that's what I'm going to show you right now. Just like back in linear momentum days, we did pi equals pf, li equals lf, and L stands for angular momentum initial, is the I. LF is angular momentum final. You can call this L1 and L2, just whatever you want to call it. It is a vector. Counterclockwise would be positive angular momentum, and clockwise would be negative angular momentum. So let's just take a look at this, and that's not really going to come into play for us right now because we're talking about planet Laurentis here, and then some later time over there. And so let's take a look at this. So we say, all right, planet Laurentis has some initial moment of inertia, and it's moving with some angular velocity, omega initial right here. We don't know what it is, but I'm just going to write that down. But we know if there's no outside torque, remember back in the day, if you had an outside force on a system, it could change the delta P, we call that impulse because you're changing the momentum of the system. Well, instead of an outside force, if there were an outside torque, like a force acting at some radius right here, if there's an outside torque, you could change the angular momentum of the system here. But we're not applying an outside torque. We're going to say your initial angular momentum here should equal your final angular momentum out there because there's no outside torque. Okay, so this should be a true statement as long as there's no outside torques being applied for a certain amount of time. All right, so we're going to treat the planet like a point mass. And you know, we treat lots of things like point masses. Planets are point masses. If you look at a human from really far away, maybe a point mass. In the later example, I'm going to treat a human like a point mass. Maybe that's not fair, but I'm going to treat the human like a point mass. So we're just going to write this out here. So the formula for a point mass is mr squared, and this is r initial. mr initial squared times omega initial. So we just, I initial became that. And then over there, something kind of cool, the mass isn't changing. So the moment of inertia isn't changing because the mass is changing. The moment of inertia is changing because this r is shrinking right here. Rf is less than ri. And as soon as we see that rf is less than ri, you're like, oh, it's getting closer. That means that planet is going to be moving faster. And you can think about stable orbits and things like that. If gravity is pulling more strongly there, that planet better be moving faster in order to maintain orbit right there. So as the radius shrinks, the planet's going to be moving faster. Let's say we're solving for omega final. Then we know that should be greater than omega initial. So when you go through and do it, you do your simplification, the m's go bye-bye. you find out that omega final equals omega initial times this, Ri squared over Rf squared. And let's take a time out for a second because I didn't give you any numbers. We're doing all in variables today. We know that Ri is greater than Rf. So we know this ratio here, right here, will be greater than 1. So omega initial times something greater than 1. We know that omega final then will be going faster than omega initial. And omega, they're going counterclockwise in the positive direction in this case. Now, one little thing, there's a different way to solve this question. If you find conservation angular momentum like this very easy and it makes sense to you, I'm going to show you one other way. If you don't like that, then method 1's great. It'll get the job done. But I'm going to show you method 2 because it's good to know. So once again, if you want to do angular momentum conservation, but you kind of want to relate it in terms of linear momentum, there's another way you can relate it. You can say it's the cross product between your r vector with your linear momentum vector. So it's a cross product between those two vectors right there. And one little thing here, this ri vector is coming out boom like this, linear momentum vector is going that way. So can you picture the ri vector would be this way, the momentum would be that way, there'd be a 90-degree angle right there. So when you do a cross product, it's the magnitude of this times the magnitude of that times the sine of the angle between those two vectors. But what I'm trying to argue here is that the r vector is this way, from the sun to the planet Laurentis here. The linear momentum vector is that way, so the angle between your r and your linear momentum is 90, sine 90 is 1. All right, but basically the formula simplifies down to Ri m v initial. And then on the same side, sorry, I had some crossouts here because I started using 2's instead of final, but same reasoning goes here that this planet's going to the left right there. So it's got linear momentum going to the left. The r vector is going from the sun to the planet Laurentis there. And when you do the cross product, it's the magnitude of r times the magnitude of linear momentum times the sine of the angle between them. So this works out to this, and this side will be the same thing, just instead of initials, you have finals. And when you get down to this, you math it out, and you're like, v final equals your v initial times the ratio of ri over rf. You're like, well, that answer is different than that answer. And it's not different like, oh, it's wrong. It's just different that's in terms of v's instead of omega. So linear velocity, vt, or tangential velocity instead of angular velocity. Now, once again, if you like this method and you're like, I got it, I like it, it's really good, stick with that, that's great. But if I want to explore this one step further, you're like, okay, I got an answer in terms of v's, can I relate that back to omega? Absolutely. You know from before that v equals r times omega. So if you ever did it this second way, which is a fine way to do it, it's the cross product between your r vector and your momentum vector, and I was lazy with my vector symbols there. If you want to relate back to omega, you just say, hey, v equals r omega, and the last page right here, we have our formula right there that we just derived from using conservation of angular momentum, and we're just going to say, hey, wherever I see a v, I'm going to plug in r times omega, so I do that. This is v final, so it's r final, omega final. This is v initial, r initial, omega initial. You rearrange it, you solve for omega final. Actually, you don't have to do that much rearranging, and you get this right here, which is exactly what we got doing it the first case way back a few minutes ago. So if you're like, wow, that second way is a lot, it's just really important to know that if you ever want to relate linear momentum to angular momentum, if you do the cross product between your r vector and your linear momentum vector and you get rmv, that's how the linear momentum is related to the angular momentum. It's just basically r times the linear momentum term there. Remember, momentum equals m times v. Being really lazy with my vector symbols here and here because that's a cross product, which gets you this right here. And if that's bothering you, you can say, hey, ri cross p I would be equal r times p, the magnitude times the sine of the angle between those two vectors. And remember, p equals mv. And we already argued that sine of theta, it's the sine of 90 because r is going that way, p is going that way. So we have, that sine 90 is this one. So you get the cross product equals rmv, just like that. All right, we're just gonna wind it down here. You have those different methods. If you're like, I really like method 1 better, that's awesome. You don't need to master every single method of everything. I just wanted to give you an alternate way you could do that. The last example we're gonna talk through here, I just want to remind you, it's very, very, very important. It's a huge concept. Back in the day when we were doing forces, right, we said F equals m times a. And if I said you had a shopping cart, you put a force on there, and I said you added some cans of soup to your shopping cart, you'd just say, oh, I added more mass. You just add the masses up, and more mass for a given force means you're going to have less acceleration, right? Because as m goes up, the a goes down for a certain force. Well, remember with rotational stuff, all of your masses, instead of just saying mass, we have to talk about moments of inertia. And moments of inertia depend on mass, but they depend on how that mass is distributed about an axis. So instead of just adding up masses like we did in the day, we can actually add up moments of inertia as long as they're about the same axis of rotation. So that's what I want to explore for the last couple of minutes here. So let's say you have a top view, and back in the day when I was a kid, we had these things at the park, the merry-go-round, where you could spin it and people would stand on the merry-go-round or sit. I don't know what was safest. And I think eventually they got rid of them because they weren't as safe as people thought. So you have a solid spinning disk, and the moment of inertia for a solid disk is just 1/2 mr squared. And you can kind of picture that, like we can reason that out, right? Because a disk, you have mass here, 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 you have mass all the way out to the rim of the disk here. So if you want to picture it like it has a lower moment of inertia, it's 1/2 mr squared, because like the average mass is halfway out there. And that's kind of hand wavy. But with a hoop, when all the mass is on the outside, that has a moment of inertia of mr squared, because on a hoop, all the mass is concentrated on the outside, so it's got a larger moment of inertia. So a solid disk is 1/2 mr squared. So we have that moment of inertia of a disk. And it's spinning, but now you want to put a person on there. And I'm going to say that person is going to be right on the edge of the disk right there. And I'm just going to treat that person like a point mass. And the formula for a point mass is mr squared. And on whatever test you're taking, they'll have to tell you, hey, you can treat the person like a point mass, or the moment of inertia of the person is this, or maybe they're going to add another shape on there and they give you a different moment of inertia. But here's the big deal. Your initial moment of inertia is 1/2 mr squared. That is just of the disk right there. Plus, you're adding this little mr squared right here. That's the formula for a point mass. And the r's in this case are the same, because in this formula for the disk, r is the radius of the disk, and the person happens to be standing on the very outside edge of the disk right at r. So the person's moment of inertia plus the disk moment of inertia gives the total moment of inertia of this new system right there. So just something really important to keep in mind. Maybe you had another person here, another person there, another person there. You can keep adding up the moments of inertia. And that kind of makes sense, because just like applying a force to a shopping cart, as you added mass, the A went down. Well, if you keep adding moments of inertia, so that moment of inertia gets bigger and bigger. Remember, in this case, when you sum your torques, it's equal to I alpha. Well, if your moment of inertia is getting very large and for a constant torque, then you can't angularly accelerate as fast. So just something to consider. They're going to give you different shapes, and they'll say, hey, in 2018, they gave you it was a free response question they released, and so it's okay to talk about. The AP people said, hey, you have spokes on a bike tire, and each spoke has a moment of inertia of something. I forget what they said. And so you had 3 spokes, so you had this spoke plus this spoke. It was a shape something like this. So you had the moment of inertia of the hoop plus the moment of inertia of this, plus that. And it was totally legit to add up the 3 spokes, 1, 2, 3, plus the moment of inertia of the hoop to get the overall moment of inertia, because they're all rotating about the same axis. So just to recap, angular momentum, you're not going to use it for collisions. You're going to use it when maybe you have an orbit, like an elliptical type path, or something spinning, and there's not an external torque on the system. So Li equals Lf, and then you go through. Remember back in the day we said P equals mv? Well, remember your m's become i's and your v's become omegas. So this is very much the rotational analog to Pi equals Pf from back in the day. But then we went through, we said, hey, you're closer here, so that means you have to be running faster. This planet will actually have more kinetic energy at this point, because it's going to be going faster at that point than it was over here. Okay, so that's a nice little introduction to angular momentum, and that's about as tough as they get there. And then we finished by talking about how, as long as you have moments of inertia that are rotating about the same point of rotation or axis of rotation, you can add up the moment of inertia of whatever object you have plus the new object there. And you can keep doing that as long, the sigma, you can add it up as long as they're about that same axis or point of rotation right there. So thanks for watching. I hope that helps with angular momentum. We're going to get a lot more practice with this, so keep rocking.